Welcome to NPTEL online course on fractals and multifractals. So, in our last discussion, we have investigated the physical interpretations of Hausdorff viscosity dimensions. So, in this class, we are going to define Hausdorff dimension in a mathematical way. So, the Hausdorff dimension a mathematical treatment. So, let me define some preliminary which needed to define the Hausdorff dimension. So, if U is any non-empty subset of n dimensional Euclidean space R power n, the diameter of mu is defined as supremum of distance between 2 points where x and y belongs to mu. We are taking the n dimensional space R power n with the Euclidean metric norm. So, this metric is defined as, I am just reminding once again, the distance between any 2 points is defined as x minus y, modulus of x minus y is defined as sum of I equal to 1 to n xi minus yi power 2 power 1 by 2. With respect to this one, it forms the Euclidean space. We are considering n dimensional Euclidean space. The diameter, if you are taking any element u belongs to this set, the diameter is defined as, find the distance between all the pair of element in the set mu and take the supremum. That supremum we can call it the diameter of the set, the greatest distance apart of any pair of points in mu is called the diameter of mu. If mu I is a countable or finite collection of sets of diameter at most delta, mu I is a countable collection of sets of diameter at most delta that covers F. That means F is contained in union of I equal to 1 to infinity mu I. As we already mentioned in the Hausdorff dimension, we are taking the cover with utmost delta. Here we are taking mu as a countable collection of sets of diameter at most delta that cover the set, the balls with the radius, different radius at most delta which covers the set F. We know that the diameter is, that means we are finding the distance function is greater than 0, greater than or equal to 0, but we are taking the supremum, it is strictly greater than 0. The norm of modulus of mu I is greater than 0 and less than or equal to delta of delta for each I, less than or equal to delta, not equal to delta. If you are taking all the boxes as equal, it is a subclass, not the high subclass of this family. We say that mu I is a delta cover of F. We can say mu I is a delta cover of F. Suppose that F is a subset of R power n. F is a subset of R power n and S is a non-negative number. S is a non-negative number. For any delta greater than 0, we define H delta of F power S is defined as infimum of sum of I equal to 1 to infinity mu I of S, such that for all this collection mu I is a delta cover of F. We know that for the F we have the many collection, for because F we are covering by the mu I at most delta cover, it has the many cover, infinitely many covers. For each cover we find the diameter of mu, mu 1, mu 2, mu 3, after mu 1 is one collection, mu 2 is other collection, like that we have many collection. In each collection we are finding the diameter. Among all the diameter we are taking the infimum, that infimum we are denoting as H delta S of F, H delta S of F. Thus, we look at all cover of F by sets of diameter at most delta and seek to minimize the sum of s power of the diameter. See this figure. Suppose this is our F. This F has the, say for example, there are two covers. F we have this one cover, this one cover. From this cover you can observe that the balls are not in the same size. This size and this size are different. Similarly, here balls have the different sizes cover the set F. So, this is one cover of F and this is also other cover of F. A set F and two possible delta cover of F is given here. The infimum of sum of mu I of S over all delta cover mu I gives this one. This one will get this quantity H delta of S, S of F, H delta S of F. I can call it as Hs of F. Now, we need to show that whenever this delta is increasing, the delta is increasing, delta 1 less than delta 2, then H delta 1 of F is greater than the H2 of F. That means it is monotonically increasing as delta tends to 0. Whenever this delta tends to 0, this quantity is increasing function. It is not, if it is increasing, this is decreasing. That means this is a monotonically increasing whenever as delta tends to 0. So, it is observed that if whenever this boxes of size delta is reduced, the number of cover will increase. This one we need to keep in mind. Now, for proving this one, let take the delta 1 less than delta 2, both are positive real numbers. Compare the admissible cover, that means let C delta of F denote the collection of all possible delta cover of F. Since every set of diameter less than delta 1 also satisfying the diameter delta 2, because if you are to cover the, if you have the set this F, if you are covering the set F by the set of diameter delta 1 like this one, delta 1 is the smaller size, then delta 2 can take the larger size. Maybe I will take other color to distinguish both. If I take that, this is the delta 2 cover. So, since every set of diameter delta 1 also satisfying the diameter less than or equal to delta 2. See, if you are taking this one, the utmost this delta, this box size is, or this ball size is delta 2. In this one, if you are taking the green one also satisfying the delta 2 condition. Therefore, every set of diameter less than or equal to delta 1 also satisfying the diameter less than delta 2. Therefore, this collection C delta 1 of F is contained in C delta 2 of F. Then key infimum, that means we need to infimum property. We use the fact that for any real valued function g, if A is contained in B, then infimum of A is greater than the infimum of B with respect to this real valued function g. This holds because enlarging the set of admissible value can only decrease or keep unchanged the infimum. Now, apply this property here. By the definition, Hs of F is defined as infimum of all the mu I possible covers belongs to C delta of F. Take the sum of mu I of S. We need to find the infimum among all this one. This is Hs. Using the step 1, the infimum property from step 2 we obtained. Step 1 we can apply in the step 2 and we obtained H delta 1 of F greater than the H delta 2 of F with respect to the same S. It is greater than. Therefore, H delta of F is monotonically increasing as delta tends to 0. Whenever your delta is approaches to 0, this is increasing quantity. This is increasing quantity. As delta decreases, the class of permissible cover of F in the equation 1.1 is reduced. Therefore, the infimum decreases. The infimum decreases, and so approaches as limit as delta tends to 0. We write this one as, if delta tends to 0, H delta S of F, we can write Hs of F, Hs of F. Now, the limit 1.2 exists for any subset of F in R power n. The limit, this limit exists for any subset F in R power n. Though the limit value can be 0 or infinity, we call this Hs of F the S-dimensional Hausdorff measure of F. We call this Hs of F as the S-dimensional Hausdorff measure of F. For early discussion, we proved that if delta 1 is less than delta 2, then H delta 1 of F greater than the H delta 2 of F. Thus, delta tends to 0, the function is monotonically increasing and bounded below by 0, bounded below by 0. By standard resultant analysis, every monotonically increasing and bounded below function has a limit, possibly infinity. Hence, Hs of F belongs to 0 comma infinity. This value is belongs to 0 comma infinity. Therefore, any subset of F, this is existing. Why the value usually 0 or infinity? Why this value Hs of F is usually 0 or infinity? Hausdorff measure is highly sensitive to the parameter, this parameter S. If S is too large, then the diameter power S becomes very small, so that the total sum tends to 0. If S is too small, this S is too small, the convergence become too expensive and the sum diverges to infinity. So, only at a critical value of S, only at the critical value of S, thus only typical obtain a meaningful finite positive value of Hs of F. So, let us try to prove that Hausdorff measures is an measure, because we already mentioned that it forms the measures. Let us try to form that quantity Hs of S forms the measure, then we can call it as a Hausdorff measure. Let us prove. For proving that H of S is a measure, we need to prove the three property. The first one, for every delta greater than 0, the empty set admit the trivial delta cover, that means no set. Hence, the covering sum is 0. So, Hs of delta, Hs of empty set this phi equal to 0 for all delta greater than 0. For any delta cover, the H delta S of empty set is 0. So, this is true for all delta. So, taking the limit delta tends to 0 gives that Hs of empty set is 0. So, Hs of empty set is 0, the first one. The second condition, the monotonicity. That means, if E is contained in F, for every delta greater than 0, any delta cover of F is also a delta cover of F. Suppose we have the set E here, this E is contained in the set F. Suppose if you are finding the delta cover for this set F like this one, then obviously this delta cover covers the set E. Hence, H delta S of E can be written as infimum of all mu I belongs to this all the cover of E summation mu I ui of power S less than or equal to infimum of ui belongs to all the cover of F. Here ui belongs to all the cover of all the delta cover of E. Here mu I belongs to all the delta cover of F summation modulus of ui power S. Since all the delta cover of F is a delta cover of E, therefore this cover, the cover of E contained in the cover of F, therefore the less than or equal to hold. So taking the delta tends to 0, we get Hs of E less than or equal to Hs of F. So like that we proved that E is contained in F, then Hs of E less than or equal to Hs of F, the monotonicity. The third one, if you want to prove Hs of SS measure, then we need to prove the countable additivity. Let Fi be a countable collection of disjoint Borel sets. Instead of this disjoint Borel set, if you are taking the general set, then we need to prove that countable subadditivity. If we want to prove Hs of as a measure, we need to find the empty set as the measure 0. And the second one, if E is contained in F, we need to show Hs of E is less than or equal to Hs of F. The third one, if you are taking the disjoint Borel set collections, countable collection, we need to show the countable additivity. Instead of the disjoint Borel sets, if you are taking the general set, we need to show the countable subadditivity. Now we are taking the disjoint Borel sets, that the Borel set is the member of the sigma algebra. If epsilon greater than 0, for each I, choose the delta sufficiently small and a delta cover mu I j of Fi such that this ui, this collection less than or equal to modulus of ui j power S, where this summation running over j is less than or equal to Hs of Fi plus delta by 2 power I. Since all these collections are delta covers, their unions form the delta cover of the collection of union of the collection of Fi. Hence, the Hs of this union, this quantity union I equal to 1 to infinity Fi is less than or equal to Hs of Fi plus epsilon. Since epsilon is arbitrary, when Hs, this quantity becomes Hs of union I equal to 1 to infinity Fi less than or equal to sum of Hs of Fi. So now we proved the one way, now we need to prove the other way. This is less than or equal to this quantity. For proving the reverse part, conversely, let Uk be any delta cover of union of Fi. Define Uki equal to Uk intersection Fi. Uk be a any covering of union of Fi. We are defining Uki as this Uk intersecting Fi. We are defining Uki. Then each Uki with this sequence is a covering of Fi and satisfying this quantity. This diameter is less than or equal to diameter of Uk. Therefore, the sum of this quantity power S is greater than or equal to sum of this quantity power S. taking infimum over all covers UK gives Hs of union of I equal to 1 to infinity Fi is greater than sum of Hs of Fi, because this is the covering of union of Fi and this is the covering of Fi's. So, you will get this inequality. So, combine this, you can take as 2, then here equation 1, then from this 1 and 2 one can conclude that Hs of union of Fi is equal to sum of Hs of Fi. So, we already proved that Hs of empty set is 0 and Hs of E less than or equal to Hs strictly less than Hs of F when this E is contained in F. Now, we are taking each Fi is the collection of disjoint Borel sets. Each Fi is the collection of disjoint Borel sets. So, this satisfying this inequality, from this 3 one can conclude that with the F at Hs is a measure. In particular, Hs of empty set is 0. If E contained in F, then Hs of E less than or equal to Hs of F. If Fi is any collection of or any countable collection of disjoint Borel sets, then Hs of union of I equal to 1 to infinity Fi can be written as sum of Hs of Fi. So, Hs satisfying these 3 conditions, therefore, we can call Hs is a measure, that measure we can call it as the Hausdorff measure of dimension S. In particular, more precisely, if F is a Borel subset of R power n, then Hn of F is defined as Cn volume power n of F, where the constant Cn 5 power n by 2 over 2 power n times n by 2 factorial is the volume of an n dimensional ball of diameter 1. Now, Hausdorff measure and the classical geometry with the comparison we can discuss. For a nice low dimensional subset of R power n, Hausdorff measure agree with the familiar geometric quantities. That means H0 of F gives the number of points in F, counting measure. H1 of F gives the length of a smooth curve. Here we are changing, the set is fixed. Here H1 of 0 gives the number of points in F, H1 of F gives the length of the smooth curve, and H2 of F is proportional to the surface area of a smooth surface F, that is H2 of F equal to pi by 4 times area of F. H3 of F is proportional to the usual volume, that means H3 of F equal to 4 by 3 times phi of volume of F. In general, Hm of F provides Cm times volume power m of F if F is a smooth m dimensional submanifold of R power n. Now, let us find the H measure for some sets in the classical geometries. So, H0 of F gives the counting measures, we will discuss here. If F is a finite set, say for example, F is the finite set in R, we can take R power n, P1, P2 up to is the Pn number of element. Then H0 of F gives the number of element in the F, the cardinality of F it will give. For H0 for F we can find, that means in the Hs of F we need to take S as 0. For S equal to 0, we have in the summation mu I of 0 which is equal to 1. The summation varies over 1 to infinity, that means for any non-empty set mu I this is 1. Then the summation counts that number of sets in the cover in the given cover. We are taking infimum among all, if you are taking 0 it will give the 1. which is equal to number of sets in the cover. So, if the set has this many x1 to xn element, each point requires at least one set to cover it. So, any cover must containing at least n sets. Therefore, H0 of f equal to 1. H0 of f equal to 1. Now, for example, if you are taking 1 to 5, then H0 of f equal to number of element in this set, which gives the value 3. Now, let us find the Hs of f for this closed interval 2 comma 5. For that, first we need to find what are the possible covering of 2 comma 5 in mean of the Hausdorff dimension. We want to cover the interval 2 comma 5 whose length is 3. If you are finding the length of this one, we can write 5 minus 2, it is 3. Use interval of size less than or equal to delta to cover this set 2 comma 5. A delta cover means each set has the diameter less than or equal to delta. In the Hausdorff dimension, we are taking the cover at most delta size. In R, diameter equal to length of the interval. The R, diameter equal to length of the interval. Here we have the length is equal to 3. So, we use interval of the form mu I equal to ai comma ai plus delta to cover this interval 2 comma 5. Each interval cover at most length delta, Now, how many intervals are needed to cover this 2 comma 5? Total length to cover is 3. We have the here 2 to 5, we need to cover this interval. Each interval contribute at most delta. If you are having mu I cover, you can take any point here, then this is one ai, then ai comma ai plus 3, you can take any number of points here, it will covers the this interval. Each interval contribute at most delta. If n interval are used, if you are using the n interval, then n times delta is greater than or equal to 3. So, n is greater than the 3 by delta. So, because we need to find the number of interval needed to cover this one with the size at most delta. So, the n is greater than or equal to 3 by delta. This must be the number of interval must be the integer. We can take the smallest integer that is satisfying previous one, that means n equal to the smallest integer of 3 by delta. So, hence n is the 3 by delta up to rounding. Then for example, if you are taking delta equal to 0.5, then 3 by 0.5 we can get 6. 6 interval needed to cover the interval 2 comma 5. So, what is the interval? Their size is delta is 0.5. If you are taking a as 2, then 0 comma 2.5, that means ai comma ai plus delta 2 to 2.5, then 2.5 to 3, 3 to 3.5, 3.5 to 4, 4 to 4.5, maybe I need to 3.5, maybe I write it here, it is 3, here it is 4, so it is 2.5, here it is 3.5, it is 4.5. So, 1, 2, 3, 4, 5, 6 interval is needed. Suppose I am changing delta as 0.4, then the number of interval needed to cover is, it is 7.5, it is the smallest integer you can take, which is greater than or equal to this number, which is 8. So, we need a 8 interval. That 8 interval you can start from delta is 0.4 to here if you are taking 2, 2.4, 2.8, then 3.2 and so on. And it goes on, then take this closed interval, it cover the interval 2, 5. Now, connect to the Hausdorff measure. We need to find the total sum. For the finding the total sum equal to sum of mu I equal to n time delta. Sum of mu I equal to n time delta. Here n equal to 3 by delta. So, n time delta is approximately 3. N time delta is approximately 3. So, recall the H1 of this H1 of 2, 5 is equal to limit delta tends to 0 H delta of 1 of 2, 5. So, now we are finding the covering. For that we have this relation. Now, we need to find the H1 of this closed interval 2, 5. For that, first H delta 1 of 2, 5, infimum of summation mu I is a delta covers. Now, any delta cover mu I of 2, 1 must cover total length 3 so that the summation is greater than 3. Hence, H delta 1 of 2, 5 is greater than 3. Now, by the upper bound, use interval of length delta to cover 2.5. The number of boxes is required to cover. We explained in previous slide. So, n equal to 3 by delta. Greatest smallest integer of 3 by delta. Smallest integer function of 3 by delta. Now, from the construction, sum of mu I equal to n time delta. Then, since n is less than or equal to 3 by delta plus 1, we obtained sum of mu I less than or equal to 3 plus delta. 3 plus delta. Thus, H delta 1 of 2, 5 is 3 plus delta. If this is a bounds of H delta 1 of 2, 5, that means which is strictly greater than or equal to 3 and less than or equal to 3 plus delta. This quantity is greater than 3 and less than the 3 plus delta. Delta is arbitrary, which is tends to 0. This delta is arbitrary. If delta comes to 0, both the side is becomes 3. Therefore, this cover we can get 3. So, H1 of 2, 5 will give the length of the interval. So, usually the first one, that H1 of 2, 5, if you are taking any set k in R, if you are finding the H1, it will give the length of the interval. Now, in R power 2, we can take this rectangular grid. That means, this rectangular grid we can take 0, 2, 0, this is 2 I can take, and this is I can take as 3. Then this rectangular grid we can take, this region we can take. So, you can see that consider f equal to this region. The area of f is, we have here side, this length is 2 and this length is 3. If you take the product, you will get the area of f. Now, we need to prove that H2 of this one is 6. The H2 of f is limit delta tends to 0 H delta of f. So, here we need to take the all possible cover and take the infimum. Instead of s, we need to take 2. Now, any delta cover mu I of f must cover total area 6. If you are finding any delta cover, must cover this total area 6. Hence, this sum of this quantity is greater than or equal to 6. Therefore, H delta 2 of f is greater than 6. Now, upper bound construction, like in the in R we are taking 2, 5 and obtained the upper bound. In same manner, covering f using square of side delta, the number of squares needed to cover this rectangular grid is n equal to 6 by delta square, take the smallest integer. Then each square has a diameter less than or equal to delta, therefore mu I power 2 is less than delta power 2. Therefore sum of mu I power 2 is equal to n time delta power 2. So n is less than or equal to 6 by delta power 2 plus 1. So again by same setting we can get like a previous one, we can get this quantity is less than or equal to 6 plus delta square. We have this is greater than 6, is delta is arbitrary. Whenever this letting 0, delta tends to 0, this quantity is get to 6. This quantity is 6. So the area of this rectangular grid is 6. Whereas if you are using H2 of this one also gives the 6. So H2 gives the area of the surface, Now let us move to the higher dimensional space. If you are compute the H3 in the higher dimensional space 0, 2, that means here we are here we may take like this one. Here we can take this is 2, this is maybe this is 2, this is 3 I am taking here, and 4 may be here. Then the all are positive in the positive quadrant, it's look like, and one can get this type of the cube one can get. Then each of its side length, this side has 2, this side has 3, height is 3, and this has the 4. That means if you draw like this one here separately, if you draw separately like this one, to draw like the cube like this one. So this has the x axis has the length 2, the height is y axis has the length 3, then this has the 4. Then if you are multiplying this one, we can get the volume of this cube. Now Hs of H3 of F, by the definition, this is the things we need to take the sum of mu I power 3, take the infimum or all possible delta cover. Any delta cover of mu of F must cover total volume 24. Therefore this sum mu I power 3 greater than 24. Therefore this H delta of F power 3 greater than or equal to 24. Therefore the number of cubes of side delta is required to cover this volume. This cube is 24 by delta 3, take the smallest integer. Then each cube has the diameter less than or equal to delta, mu I power 3 of delta less than or equal to delta power 3. Thus sum of mu I power 3 equal to n time delta power 3. Therefore n is less than or equal to 24 over delta power 3 plus 1. Then we obtained sum of mu I power 3 is less than or equal to 24 plus delta power 3. By comparing this, we can get this one. Then the upper bound one can get 24 plus delta power 3. This is 24. Again, if delta tends to 0, this convergence is high. Therefore, it compared with the 2, 5 in the interval and real number, this goes to number 24. So one can get the volume of equal to 24. So by taking a H3, one can get the value is 24. So you can see in all our 3 example, H1 of 2, 5 gives the interval length, and 0, 2 and 0, 3. This cube if you are taking, it gives the area, and if you are taking this one, this cube, it gives the volume. That means h1 of 2 comma 5 we are getting as 3. It gives the length of this interval, and h2 of 0 closed interval 0 comma 2 cross 0 comma 3, we got it 6 as the area. If you are applying h3 of this set 0 comma 2 cross 0 comma 3 cross 0 comma 4, we got it is 24, we got the volume. So this Hausdorff measure, if you are running one dimensional Hausdorff measure will give the length of the set, two dimensional Hausdorff measure gives the area of the set, and three dimensional Hausdorff measure it gives the volume of the given set. Now let us try to find the Hausdorff measure for the Cantor set. First, in the 0 dimensional measure, that means we can find the number of element in the Cantor set. H0 of C count the number of points in C. The Cantor set is uncountable set. So hence H0 of C is infinity. Now one dimensional measure for the Cantor set, we are finding the 0 dimensional, it is infinity. Now we are finding the one dimensional measure at any step n. C is covered by 2 power n interval, each of its length is 3 power minus n, right? Because I just recalling here the Cantor set is formed by starting with the initial line segment, dividing 3 equal parts and removing the mid one. So after the first step we will get this one and 2 by 3 comma 1. So and so on, we need to continue. So the Cantor set C is covered by 2 power n interval, each of its length is 3 power n. For example, here we need 2 sets, we need to cover this one, each of its length is 1 by 3. This cover is 0 comma 1 by 3, this is 2 by 3 comma 1. So we need this is at the first step. So in the nth step we need 2 power n intervals, each of its length is 3 power minus n. Therefore sum of mu I is number of interval time its length. So 2 by 3 power n. So if n tends to infinity, this goes to 0. If n tends to infinity, this goes to 0. Hence h1 of s we can conclude it is as 0. Now this we can note that for the Cantor set, if you are finding the 0 dimensional Hausdorff measure, it is infinity. 1 dimensional Hausdorff measure, it is 0. So as we discussed in the last lecture, you can take a set, that means you can take a line segment. For the line segment, if you are finding the area, it is 0. Number of points, if we are finding, it is infinity. Therefore length is the suitable measure. In between 0 and 2 there is a number 1. If you are finding the 1, that Hausdorff measure becomes the positive and finite number, that we can call it the length of the interval. And in r power 2 we take the surface. In the surface we are finding the area, it is a finite number. If you are finding the volume, it is 0. If we are finding the length, it is infinity. Obviously if you find the number of points, it is also infinity. So in between 1 and 3 there is a number 2. If you are finding the 2, we are finding the area. So the area is a suitable measure for this surface. So whenever there is some critical point, after this if you are increasing the s value, we are getting 0. Whenever the s value is less than this critical value, we are getting infinity. So, here in the Cantor set also we can observe that the H0 of Cantor set is infinity. That means this 0 gives the infinity, H1 of C gives the value 0. Now, you can observe that in the classical Euclidean geometry, Classidian object, we are taking the line segment, maybe this interval we can take. If we are finding the H1 of C, we are getting 1. If we are finding the H2 of this, I can call it as C, the C I am getting infinity, the H0 of C I am getting, sorry, H2 of C is 0, H0 of C is infinity, which we discussed in the previous lecture. This is the line segment. For the line segment, if you are finding the length is a suitable measure, whereas number of points and the number of points is infinity, the area if you are finding 0. So, here you can observe that 1 we are getting 1 and 2 we are getting 0 and 0 we are getting infinity. That means 0 it goes to infinity, in the 2 it goes to 0. So, in between 0 and 1 there is an integer number 1 which we associated with this Hausdorff measure, which is the finite value of this interval, that we can call it as a length of the interval. Now, you can observe that if you are giving the value 1 for the Cantor set, it goes to 0. If we give the value of S as 0, it goes to the value infinity. Now, the question, in between 0 and 1 there exists a S, is there any S between 0 comma 1 which gives Hs of C as a finite number? Is there any such a number? Now, based on this we are going to define what is the Hausdorff dimension, that critical value. Yes, there will be a point existing in between these two integers that will make the Cantor set as a finite, S dimensional measure is finite, that yes, the critical value we are calling as the Hausdorff dimension, that we will discuss in the next class. So, here I am stopping. This leads to the definition of the Hausdorff dimensions. In the summary, if you are taking the usual object in the Euclidean objects, if you are finding the S dimensional Hausdorff measure, there is a shifting point, there it is a finite, but the shifting point is an integer. In the fractal object, the shifting point is the non-integer. That non-integer value we are calling as the Hausdorff dimension, that we will discuss detailedly, define in the next class, and find the Hausdorff dimension for the classical object as well as the fractal object with some basic properties. Thank you. One can refer these books for the more detail. Thank you.